All right, good morning, everyone. Today I have another episode for you about the little compiler and interpreter we've been writing. Today it's going to be a little different. I wrote a bit of code in advance, and so we're going to look at what I did really quick. I'm going to run a little time lapse. I'll explain roughly what I did, and then we can go look at the code itself. It's just quite a lot of stuff that had to be written, and I didn't want to fill 2, 3, 4 episodes doing it. Even if it maybe wouldn't have taken that long, I just wanted to make sure it's not that long. So let's get into it. The first thing we do here is we basically add all the other instructions that are in the specification or in the reference to the tokenizer. So this is just basically a fancy copy paste of all the instruction names in their string versions. And then we start implementing them. So specifically, we have to implement a lot of arithmetic instructions. And the way that I've designed this is that you have a value integer, and that's the only thing that exists. But in the future, there's going to be string values and other values. So it's pretty important that we actually build support for this into the whole system to ensure that later when we add other data types, it's not going to blow up in our face. So what we're going to do here right now is basically just write big if-else statements to check the type. And a bit later, we're going to refactor this. But basically, we just make those big if statements, if-let statements, in order to pattern match on that there is a value on the stack and that value is an integer. And now I've realized basically, yeah, okay, this sucks. I'm not going to write this a million times. So I wrote a little function that I had a very difficult time naming, which is basically an apply function, apply a function onto the top two stack elements. And basically doing is popping two things off the stack, type checking them, and then performing an operation on them. I've made that a function because I felt that was the easiest way for it to be still readable code. No arcane bullshit, but at least it is a function. And so you can see me adding a more complicated one there. But we'll look at that in a little bit. As I said, we'll go through this code. I'll explain everything, but I just wanted to show you the time lapse of, I actually did write this myself. So there's in the division case and in the modulo case, there's of course an if check on every element to ensure that we don't divide by 0. That's a pretty important thing. So I built that in there as well. And I made 2 separate errors for it, mod by 0 and div by 0. And that's pretty much all that I've written so far. All right, now that we've seen that, let's look at the code and let's jump into actually programming here. Let me adjust my light. So, okay, we have our, was it interpreter? Yeah, there it is. So here's a few things that I want to actually talk about. So let me just hide this really quick. So a few things I want to make clear and talk about here. The first thing is, as I said, we've implemented a function to do transform top to integers, which is basically just applies this function onto the top 2 elements of the stack and returns an error if there's any problem, like there's the stack's empty, whatever. If wrong type, but there's like the invalid type error, and then the pop stack top, as we recall, actually returns a stack empty error. So these are both errors that can be returned, and then we start actually looking at the code and we see that this is a if-let, another if-let. Now we'll see if this is performed. Probably not, right? So we might have to just speculate and just kind of start writing, like just kind of do an addition and see what happens, because right now we run into the Python performance problem where you have things and you don't know what type they are. So it might be worth having the compiler type check so that we push things onto the stack and the compiler would sort of keep track of it and ensure that if you push something onto the stack and then immediately pop it, that there's a type check, basically. We could do that It gets a little bit more complicated once we implement more instructions, and especially if we ever implement function calling, for example, it gets a little bit difficult, but I think we can do it. I mean, if we add strong typing anyways, like static typing, then we might as well, because right now it's dynamically typed, and I don't like that. It works for us right now, and it's going to keep working for a bit, but once we get into performance optimization, we might have to make some significant changes to the compiler to make it type check everything, because that might just be the only way. Okay, so we have transform top two integers, which takes a function that takes two integers and returns a result, the resulting integer, which we can then push again or do whatever we want with. I think we do push it actually. Do we push it? Oh, we do push it. Right. So we also return. The function returns it and we push it. Right. Yeah. So we push back the value that we return here. And as I said, this is probably wildly inefficient, but again, if you have performance problems, you profile, right? Making assumptions about your performance is usually a terrible idea, and you're usually wrong. This stems from humans not being very good at just executing code in their head, so we end up just fucking up and thinking that the wrong thing is causing a slowdown. There's some examples I could pull out my ass for that if you want, but I think it's fine. And there's transform top integer. So these names are terrible, and as I said, we're going to probably replace these, but right now we need them so the code stays clean. This does the same as the other one. We pop one value, we modify it, we push it back to avoid a push and a pop that we don't need. We actually just take a reference to the top of the stack, modify the top of the stack in place by having a function that just takes a mutable reference to the stack top. So, for example, this is used in the increment and decrement instructions, where we pass in a function that just increments or decrements the number. The add instruction looks like this, for example. So we return an OK of a plus b. The reason we have a result type here is because, for example, as I said before, division can fail. If we're dividing by 0, we want to check for that. So because we don't want it to like panic or whatever Rust does, not intended to find out. So if we divide by 0, we throw divide by 0. If we mod by 0, we throw mod by 0, as I said. Repeating myself, I didn't implement these because these are actually interesting enough to implement on camera together. But I just wanted to get these out of the way. And let's write a little program. Let's ensure that this actually built and I didn't mess up. Okay, so let's look at the test.mcl program. So we have this push and we have this push and we add them together. And this works. So let's see. Compile exec test MCL, but we'll change this whole thing. The whole command interface will change. It's just for development right now. Let me have some coffee. We're having instant coffee without milk once again because we're fancy like that. Beautiful. Happy. I'm so happy. Okay. So yeah, 1001 plus 999 is 2000 if you do the math. If you're a smarty pant like me and you can do the math in your head like that. Of course, we can subtract. And oh, is subtract not implemented properly? I think we fucked up. Well, I fucked up. I think we didn't implement all of the things in the compiler. Actually, we might have missed them. Yeah, we missed this. Okay, so we do need to add this. So I'm curious, could we... I'll need some feedback in the comments on this one. Could we have a rule where we basically say op and then is it like a where if u64 or u8 or what is it, op as u8 less than, I don't know, let's just pick something. Can we do that? I mean, I know that this doesn't work, but I'm trying to figure out if you can get an if statement. Let's look this up. So Rust, what was it? Match. Let's just look at the syntax for the Rust match. Let's see, so we get match arm, expression without block, expression, match arm guard. That's probably what we want, right? We want a match arm guard, which is an if expression. Okay, let's have a look at the match guard. So this is sum x if x less than 10. Okay, so let's actually do this because this is interesting. So as you might have noticed, and I might have actually said this before, the operations, the opcodes, they are ordered. And so they're ordered so that all the ones that don't take an argument come first, and then all the ones that do take an argument come after. So we really can just compare against push. If the instruction is less than push, it doesn't require an argument. If it's more than push, it does. So we can wildly optimize this whole bullshit to just that. And then we just need to do a little bit of magic. We need to do this is our op. And then we need to say if, how do we do wrapper? Let's look that up as well. So Rust enum to wrapper. I thought it was just, what the fuck? Why is there ads here? Oh, whatever. Whatever. We'll just swallow the ads right now. Doesn't matter. Figure it out later. This is not what I want. Yeah, this is what I want. Suppresses no. Yeah, I don't really know what that's supposed to mean. I mean, I know what that's supposed to mean, but match enum with it. Oh my god, got flashbanged. Jesus Christ. Also, you can tell I'm German by the way that it thinks I'm in Germany right now. I mean, I am, but my whole system is in English, so I don't really. It's as, isn't it? Can we do that? Can we just say if as, what do we say, U8? Expected bool. Okay, so if that is less than op push as U8. So if it's less than op push, not including, so less than, then it's this. Can we just nope. Okay. And then the other case, that's the one where it's bigger or equal to, right? So this is, you have we want to probably put this down here so it's a little bit more easy to see, where if op as U8 is bigger or equal to op push as U8. Actually, do we have to do as U8 or can we just compare them like this? I think we should be able to just compare them like this because we can implement I think we can implement partial equality, partial ordering, and that should do it. Yeah, then we don't have to do this. That was a brain fart on my part. Sorry about that. Because partial ordering is exactly what we need. We only want less than ordering, pretty much. Okay. Can we like split this up? This is a little bit much, to be fair. No, it doesn't like it. Okay. So, and then here we need to actually push that instruction. So this means that now we don't have to add all the instructions to this. We just need to follow this convention. Horrible. Okay. There's probably a better way to do this, to be fair, but this is exactly what the other one does. So let's just do it like this. Okay, so now it works. Now we do sub and 1001 minus 999 is 2. If you do the math, works out to be 2. So let's do a different one. I want to see what happens. It should be fine with just yeah, -2. So negatives, just no problem, of course. The only thing that is a problem is negative literals, because it's not going to actually parse them as negative literals, will it? It does parse them as negative. Why does it do that? It does that because I thought we truncated that, but I guess we don't. How do we... So the reason I'm confused is because, as I said, I think last time was it, that we do truncate the value, right? Because so we convert it to an I64, but what happens next in the, where is it, the instruction, once we actually do take the instruction and encode it or decode it, we do this, and I feel like this shouldn't work. Right, because if it's 2's complement, which it is, then the first bit, which we nuke, is gonna be, yeah, here we nuke the first, we nuke the sign bit, don't we? I thought we did. Did we not? Let's just compile and see what happens. Like, so yeah, here it's still negative, obviously. So let's hex dump the test mclb, the binary file. This is it. Okay, yeah, and okay, we'll have to look at this later because that confused. I mean, I'm glad it works, but I feel like something's wrong. Some bug is, maybe it's not the bug where we lose the sign bit, but something's fucky. I don't like it. Okay, so now that we have them, we can actually use them. So let's try a few others. Let's try the see how, what should we try? Let's get positive again. Let's increment a few times. Let's decrement a few times. And then let's I don't know. Just see what happens. Yeah, looks good. So we do increment here. We increment, it goes from 2 to 3, increment again, 4, 5, decrement goes to 4, decrement goes to 3, pop. Simple stuff. Works. I would say that works, and I'm pretty happy about that. So yeah, cool. Let's actually commit some of this. So in case you don't know, git commit, this is git commit dash p, which stands for pick. Is it here somewhere? Does it say? Yeah, it stands for pick anyway. So lets you basically answer with one of these to figure out if you want to commit that chunk. So yeah, so let's do that. So the first thing is this, which we do want to commit. Don't want to commit that. We don't want to commit that. We don't want to commit this. We do want to commit this and don't want to commit that. Okay, so now we make use of up ordering for argument matching. Yes. Actually, that's not okay. And then the other stuff is just formatting. Okay, now that we've done that, let's actually have the same file open twice, like in Monkey here. Okay, so let's go to the interpreter and let's start implementing something else, and then we can call it a day. Also, the first video is at 3K views, which is a little crazy. That's my most viewed video. I think the other one is at 1.6K or something. That's privated. Used to be a Let's Play channel, so whew, cringe. I mean, it's not that cringe, but it is funny that Rust happens to be my most viewed video. That is cool, I guess. So let's implement two more. So I want two more instructions so that we can start writing some interesting programs here. So halt we want to implement because if we run into the halt instruction, we simply want to halt, which is we just return, right? So we just return, okay. And also we should probably print why we are returning. Front line. Okay, so now halt will just kill it, and then dupe. So dupe instruction is very fun. This is one of the things that make more complicated programs possible, because every instruction that does some sort of transformation, except for the ink and deck, they're kind of weird. They pop something from the stack, right? So say you want to add two values together, you push one, you push two, you do add, but then you lose those two values, right? So because they get consumed in the process of adding, which is fine, that's what you want sometimes, but sometimes you actually want to keep them. In this case, you would use dup and over or something. So yeah, we want to actually implement dupe and over, I think. And then dupe2 does the same thing as over and dupe, like dupe over dupe or some shit like that. So, right. And this gets kind of complicated when you start programming in it, because you have to think about, you only have access to the top two values on the stack, and you have any access to those. You can swap them, you can copy them, you can do all sorts of stuff, but you can't go deeper into the stack. And for that, we might have to build a mechanism if we get into writing more complicated programs. We might have to do stuff like I don't know, giving you multiple stacks or some sort of fun mechanism that lets you write more complicated programs. But right now, let's just stick to, just have to check the time because I have a stand-up meeting soon, because, you know, I go to work after doing this in the morning. It is the early morning, it's 9 in the morning. So dupe instruction basically just should be pretty simple. It should be self stack push back, self stack back. We want to do we want to check if that exists. So if let top is back, then sorry about that, we push that, and else we do a return error, interpreter error, stack empty. Yeah, because yeah, okay. So let's demonstrate this. So push one, push two, dupe, add, print. So what does this do? It's a little funny, but if you're not used to stack-based languages like Forth or something, which I'm vehemently trying to avoid building a Forth, but we push one, we push two, we duplicate, which is the two, we duplicate the two, and we run an add. So at the end, we have only the one on the stack, and we added, like, well, we have four and a one on the stack. You'll see what I mean. So effectively, we push one, we push two, right? No, we don't print. I'm sorry. I missed printing this. And this should really be like a function that converts this into this. It's very simple to do, I just didn't bother yet. Okay, so push one, push two, we dupe, and when we dupe, the stack top gets duplicated. Okay, it's right here. So now we have two integers. When we add those two, and we now have 4 and 1 on the stack. Okay. And let's also try the halt for fun. just halts. So this is going to be good later for early returning, like early canceling. We will have to implement function calls probably because it gets really complicated trying to like call stuff. Well, I guess you don't need function calls. I guess you can just keep pushing onto shit. But it would be nice to have function calls that sort of where you push stuff onto the stack, then you call it with a sort of sort of like Lua does it. So you push stuff onto the stack, you call it and say, okay, like you would basically say call to, like call function to, and then the function would actually take like would get a new fresh stack with nothing except the two things that are on the stack when you call it copied on it. So that would be very useful, and we'll think about that. We'll design something like that. But the other thing is, what if I want my stack to end up being 1, 2, 1, 2, right? So I push 1, 2, but then I want to duplicate both. So what we do then is we do over and over, I think, double over. So what double over should do, the first over, we're here, goes here and duplicates this, okay? And then the second over duplicates this. So we get that. And that's what we want. So let's actually implement over, and then I think we're done for the day. And the other ones we're not going to implement right now. Okay, so over is going to be stack stack len less than 2. We want to come up with a better error for this because it's not technically stack empty, because the stack isn't empty. It's just too empty to do it over. But right now we're not going to bother with that. We know what it means when we get an over and then we get a stack empty error, right? Like it's pretty fucking clear what that means. We let so yeah, I think at this point we can just do whoops self stack so it's length, right? I'm programming Go again. It's a miserable time. Every time I program Go, I just end up writing fucking wrong code in all other languages. It's crazy. So okay. I think that should work, right? And it doesn't care about data types, obviously, right? Because it completely doesn't care. It just does that for whatever data type there is. So now let's run it. Let's see what happens. So push 1, push 2. Oh, of course, we need to print. So the reason we don't see the result is because we need some sort of we could just halt, doesn't matter. We need some sort of instruction that will run, because we only print the stack before we run an instruction, not after. So yeah, so we have 1 and 2, right? This is our initial case where we push 1 and 2. Then we over, which copies the 1 from here, and then we have over again, which copies the 2 from here to there. And an obvious optimization is, because this is a weird, like you have a length check twice, and then you have a pushback twice, and you have an access to the stack twice, right? So that's quite a lot of operations to basically just say duplicate not 1 but 2. And so that's what dup2 is. And if you recall, in the compiler, we don't actually let actually probably don't call it because I wrote this in the time lapse. Dup2 is actually not callable by the user. And we might change it, doesn't really matter. But the point of dupe2 is really to be an optimization. So we'll write some simple substitution optimization where we basically detect, do you do over twice? If you do over twice, we just replace it with a dupe2. That's it. I mean, there's other instructions like that. And then, we could continue doing that. We could continue like, if you like push and then pop immediately, we just void that entire instruction because it does nothing, and so on. We could do some funny stuff like that. But yeah, I think that was pretty good for today. I'm gonna commit this really quick. So implement halt loop over. Yeah. We'll push that and we'll look at flashbanged. The repo really quick. We also didn't make like a README, but it is what it is. Okay, and that concludes the episode, I think. I think we did pretty good there. Did it not push? It didn't push. What's the problem? Oh, I made it rested by okay. So we actually want to rebase pull that, I think, and then push that. Force push maybe. No, just push. Okay. I made it so it basically just runs a CI/CD pipeline on it, just because that's nice like that. Let's see if it actually does it. Yeah, it does it. So now it will build the rest thing. Anyways, yeah, thank you very much for watching. Make sure to subscribe because that's important, and make sure to like because that's also very important. Hope you have a great day, and I'll see you in the next episode.